Welcome to Hitchhikers TV. Let's continue to learn about Earth and space as we explore the lines of evidences that support plate movements. This video presentation would enable grade 10 students to enumerate the evidences that support plate movement as one of the most essential learning competency for grade 10 science week 8 of the first quarter lesson. Modern continents hold clues to their distant past. Evidence from fossils, glaciers, and complementary coastlines helps reveal how the plates once fit together. Fossils tell us when and where plants and animals once existed. Some life rode on diverging plates, became isolated, and evolved into new species. Other life dispersed to new areas as continents reconnected, oceans narrowed, or chains of volcanic islands formed. Finding identical or similar fossils in areas separated by vast distances were some of the first clues that scientists used to reconstruct past plate movement. This distribution of fossils led to theories that the southern continents were once joined in a supercontinent called Gondwana. Similar geologic formations on different continents show historic land connections. Antarctica's mountains are an extension of South America's Andes. If southern hemisphere continents were reassembled into a single land mass, glacial remnants in Africa and India would realign. What are three pieces of evidence for plate tectonics? There is variety of evidence that supports the claims that plate tectonics accounts for 1. The distribution of fossils on different continents, 2. The occurrence of earthquakes, and 3. Continental and ocean floor features including mountains, volcanoes, faults, and trenches. Alfred Wegener, in the first 3 decades of this century, and Dutoit in the 1920s and 1930s gathered evidence that the continents had moved. They based their idea of continental drift on several lines of evidence: fit of the continents, paleoclimate indicators, truncated geologic features, and fossils. In the early part of the 20th century, scientists began to put together evidence that the continents could move around on Earth's surface. The evidence for continental drift included the fit of the continents, the distribution of ancient fossils, rocks, and mountain ranges, and the locations of ancient climatic zones. The continental drift hypothesis was developed in the early part of the 20th century, mostly by Alfred Wegener. Wegener said that continents move around on Earth's surface and that they were once joined together as a single supercontinent. While Wegener was alive, scientists did not believe that the continents could move. Evidence for continental drift. Besides the way the continents fit together, Wegener and his supporters collected a great deal of evidence for the continental drift hypothesis. Identical rocks, of the same type and age, are found on both sides of the Atlantic Ocean. Wegener said the rocks had formed side by side and that the land had since moved apart. Mountain ranges with the same rock types, structures, and ages are now on opposite sides of the Atlantic Ocean. The Appalachians of the eastern United States and Canada, for example, are just like mountain ranges in eastern Greenland, Ireland, Great Britain, and Norway. Wegener concluded that they formed as a single mountain range that was separated as the continents drifted. The similarities between the Appalachian and the eastern Greenland mountain ranges are evidences for the continental drift hypothesis. Ancient fossils of the same species of extinct plants and animals are found in rocks of the same age but are on continents that are now widely separated. Wegener proposed that the organisms had lived side by side, but that the lands had moved apart after they were dead and fossilized. He suggested that the organisms would not have been able to travel across the oceans. Fossils of the seed fern Glossopteres were too heavy to be carried so far by wind. Mesosaurus was a swimming reptile but could only swim in fresh water. Cynognathus and Lystrosaurus were land reptiles and were unable to swim. Wegener used fossil evidence to support his continental drift hypothesis. The fossils of these organisms are found on lands that are now far apart. Grooves and rock deposits left by ancient glaciers are found today on different continents very close to the equator. This would indicate that the glaciers either formed in the middle of the ocean and/or covered most of the Earth. Today glaciers only form on land and nearer the poles. Wegener thought that the glaciers were centered over the southern land mass close to the South Pole and the continents moved to their present positions later on. Coral reefs and coal-forming swamps are found in tropical and subtropical environments, but ancient coal seams and coral reefs are found in locations where it is much too cold today. Wegener suggested that these creatures were alive in warm climate zones and that the fossils and coal later had drifted to new locations on the continents. Although Wegener's evidence was sound, most geologists at the time rejected his hypothesis of continental drift. Why do you think they did not accept continental drift? Scientists argued that there was no way to explain how solid continents could plow through solid oceanic crust. Wegener's idea was nearly forgotten until technological advances presented even more evidence that the continents moved and gave scientists the tools to develop a mechanism for Wegener's drifting continents. Magnetic polarity evidence. Puzzling new evidence came in the 1950s from studies on the Earth's magnetic history. Scientists used magnetometers, devices capable of measuring the magnetic field intensity, to look at the magnetic properties of rocks in many locations. Earth's magnetic field is like a magnet with its north pole near the geographic North Pole and the south pole near the geographic South Pole. Magnetite crystals are like tiny magnets that point to the north magnetic pole as they crystallize from magma. The crystals record both the direction and strength of the magnetic field at the time. The direction is known as the field's magnetic polarity. Magnetic polarity on the same continent with rocks of different ages. Geologists noted important things about the magnetic polarity of different aged rocks on the same continent. Magnetite crystals in fresh volcanic rocks point to the current magnetic North Pole. No matter what continent or where on the continent the rocks are located. Older rocks that are the same age and are located on the same continent point to the same location, but that location is not the current North Magnetic Pole. Older rock that are of different ages do not point to the same locations or to the current magnetic North Pole. In other words, although the magnetite crystals were pointing to the magnetic North Pole, the location of the pole seemed to wander. Scientists were amazed to find that the North Magnetic Pole changed location through time. There are three possible explanations for this. 1. The continents remained fixed and the North Magnetic Pole moved. 2. The North Magnetic Pole stood still and the continents moved. 3. Both the continents and the North Pole moved. Magnetic polarity on different continents with rocks of the same age. Geologists noted that for rocks of the same age but on different continents, the little magnets pointed to different magnetic North Poles. 400-million-year-old magnetite in Europe pointed to a different North Magnetic Pole than the same-aged magnetite in North America. 250 million years ago, the North Poles were also different for the two continents. The scientists looked again at the three possible explanations. Only one can be correct. If the continents had remained fixed while the North Magnetic Pole moved, there must have been two separate North Poles. Since there is only one North Pole today, The only reasonable explanation is that the North Magnetic Pole has remained fixed but that the continents have moved. To test this, geologists fitted the continents together as Wegener had done. It worked. There has only been one magnetic North Pole and the continents have drifted. They named the phenomenon of the magnetic pole that seemed to move but actually did not apparent polar wander. The apparent North Pole for Europe and North America if the continents were always in their current locations. The two paths merge into one if the continents are allowed to drift. This evidence for continental drift gave geologists renewed interest in understanding how continents could move about on the planet's surface.